All right, so today's lesson is 6.2, and this takes us through similar polygons. Before we can get to similar polygons, I want to quickly review an old term, and that is congruent polygons. And if you remember from the first half of this course, congruent polygon are ones that are identical. They're exact copies. They have equal angles and equal sides. And the notation was the equal with the little squiggly over it. But we could pick them up, flip them, turn them, slide them. They were exact copies. It's important to think about this when we talk about a similar polygon. Now, a similar polygon is going to be a polygon that has equal angles and proportional sides. So you're either going to blow everything up by a factor of 2, or you're going to shrink it all by a factor of 1/3, but it's uniformly blown up or shrunk. Our notation here is just the little squiggle, so it looks like the congruence one without the equal, and we're going to talk about similar being an aspect of being blown up or shrunk uniformly. Scale factor is an important term we're going to be talking about, and that is the ratio between side lengths of a similar polygon. That's how much we are going to blow it up or shrink it. So our scale factor would be 2 if we make it all twice as big. Our scale factor is 1/4 if we shrink everything by 1/4. Now, K is typically used as a variable for scale factor. So if you see what is K or K equals, they're referring to scale factor. That is the standard variable associated with that. So a quick example, are these groups similar or not? When you look at group A, obviously these two don't look like the others. This one doesn't look like the others. So these are not similar. When you look at B, every one of these could be created by doing a blowing up or a shrinking of the sides. So those are all similar. In the same manner, to move from this one to this one or that one to that one is a matter of blowing up or shrinking. And so that also represents a group of similar items. Now, congruence statements were important in the last unit because they told us that the order of vertices matched up. Similarity statements are going to do the exact same thing. If triangle ABC is similar to triangle JKL, write a congruence statement for the angles and proportions for the sides. When in doubt, draw a picture. So I've quickly sketched triangle ABC and triangle JKL. Now, congruence statement for the angles. Remember, in similar polygons, the angles are equal. And so A corresponds to J, and we see that in our statement. You can use the similarity statement that B and K are equal, and C and L. Now, when it comes time to write a proportion for the sides, the picture is also very important because I can see that side AB corresponds to side JK, both from the picture and from the congruence statement. And so when I go to start writing my ratios, I might want to make myself a little key, so I know I'm going to put triangle ABC on top. I'm going to do triangle JKL measurements on the bottom, and then I set up my ratios. Side AB relates to JK. Side BC relates to side KL. And side AC relates to JL. And I set up my proportions for the sides. Example 3 asks us to write a similarity statement for these two quadrilaterals. So we know from the last unit, we can start wherever we want. I'm going to start with this figure, and I'm going to write quadrilateral ABCD is similar to A corresponds to E, B corresponds to F, C corresponds to G, and D corresponds to H. Now, even though the markings are a little hard to see, if you look at the ratios of the sides, 5 compared to 2.5, 6 compared to 3, I'm getting a consistent scale factor of 2 And so I know I have them set up in the correct way. Now, speaking of scale factor, if I move from this figure, ABCD, to EFGH, I'm actually going to make it smaller. So I'm going to multiply by 1/2. That would be my scale factor. But if, on the other hand, I started with the little guy and went to the big guy, I would be multiplying by 2. In fact, we could talk of 2 over 1 to do that enlargement. So when it comes to scale factor, the scale factor here could be 1/2 or 2 over 1, depending on which figure is the original starting figure. So we always want to make sure to be thinking about which one is the original. Am I blowing up or shrinking from what starting point? So are these quadrilaterals similar? Why or why not? When I look at RSTQ and XYZW, the first thing I notice are these angles. So these are not similar because the angles are not equal. That's the first part of the definition of similar figures, is they have to have equal angles. Now if I go to B, the angles are equal, so I bypass that and I start to set up my ratio of my sides. You can see I kind of coded them with shapes, the square ones to the triangles, to the circles, to the underline. If you create a list of your ratios, 5/3, is that the same as 3 over 3? Is that the same as 5 over 3? Is that the same as 3 over 3? If these all end up being the same ratio, my figures are similar. Since these are not, it's not similar because the sides are not proportionate. They all have to be the same in order to be similar. Now we're going to get into some solving. I'm given that MNPQ is similar to RSTW. Find X, Y, and Z. Well, I'm going to start with Z because I see that M corresponds to R. Here's M and here's R. And since the angles are the same, I know that Z is equal to 115 because angle M and angle R are exactly the same. Now I'm going to need a basis to make my ratio. And I see that MN corresponds to RS. This piece right here to this piece right there. So I can set up a ratio of 18 over 30. From that, I can find my other pieces. X here is NP, and NP corresponds to ST. I know you're thinking you can look at it and tell that, but it's always safer to use the words over the pictures because you know that pictures lie. So I'm going to have is equal to X over 25. Cross multiply. And when I do that, I find out that X is 15. Now I'm going to go back and I'm going to continue to use this 18 over 30. I could now use 15 over 25, but if I calculated the 15 wrong, then my next one's going to be wrong. So 18 over 30 was given. I want to use that. TU is my Y value. TU corresponds to PQ, right here. I've got my smaller triangle on top, or smaller figure, excuse me, on top, my bigger figure on the bottom. Cross multiply. And when I solve for Y, I get 25. Now you could do a check by taking 18 divided by 30, 15 divided by 25, and 15 divided by 25, and make sure it comes out correctly. It's an easy way to check. Now the next picture, overlapping rectangles. Given ABCD is similar to AM and P, find BM, BC, and PD. Well, let's get a visual of what we're looking at. In these two rectangles. So if they're rectangles, which I'm going to tell you they are, that means that opposite sides are equal. It means that this side over here is also 45, because it is 45 over here. So that makes it pretty clear to be able to find BM, which is our first question. That's a matter of parts to whole. That AB is equal to AM plus BM, substitute 45 and 30, subtract, MB is 15. Pretty straightforward problem. Now to find BC, B to C, I'm going to go ahead and set up my ratios of BC and MN corresponding, and then the fact that BA and MA correspond. So I'm going to set these up. In general, BC over MN is equal to BA over MA. Substitute the values you know. I don't know BC. I know that MN is 40, because it's the same as AP. I know that BA is 45, because it's the same as CD. And I know that MA is 30, and that is given. Simple cross multiplication, divide by 30, and BC ends up being 60. Once you know that that's 60, finding PD is again a matter of parts to whole. That AD plus AP plus PD, 60 equals 40 plus PD. Substitute in the numeric values. Solve, and PD is 20. Given that ABCD is similar to LMNP, what is the ratio of their side lengths? Before we get going, we need to decide what we're going to use for K. What are we going to use for our old or for our new? If I go from this figure to this figure, I better make sure my K is a fraction because I'm making my problem smaller. If I go from this picture to this picture, I need to have a whole number or something greater, not necessarily a whole number, something greater than 1 so that I can blow it up. It doesn't matter which way you go, as long as you are consistent through your whole problem. A key to remember as we get going in this unit is that K is always the new figure over the original, or new over old. And if I make this one my original, and I'm going to move to this guy who is my new, I now can be consistent throughout all of my calculations in finding the different values. So the ratio of the side lengths is as simple as saying K is equal to new over old. We always reduce fractions. 15 is your common factor, and my K is 2/3. The ratio of the perimeters, so we're going to do the perimeter of the new over the perimeter of the original. And so the perimeter of A, B, C, D is equal to 140. The perimeter of L, M, N, P is equal to 60 plus 60 for 9, 210. The zeros will cancel. 14 and 21 have a common factor of 7, which leaves me 2/3, which is exactly the same scale factor as the length. Now, when we go to the area, we're going to do the same thing. The ratio of the area of the new versus old. So the area of A, B, C, D is 1,200. The area of L, M, N, P is 2,700. When we cancel those two and reduce, common factor, we're left with 4/9. Now, in looking at this is a bit of a preview for tomorrow's lesson. We see that the length is 2/3, the perimeter is 2/3, the area is 4/9. I'm going to leave you to think about